I will do it. So anyway, taking a look at number 53, I've got the diagram over here. Let me just move this over so that I have room to do the whole thing. There we go. Okay, so first things first, we want to draw this thing because it's always nice to know how it looks. Not only that, but on your quiz, I have the regions drawn for you, shaded. Isn't that beautiful? Those nice triangular regions, so pretty. So, so then you don't have to worry that you're going to get it wrong, at least not that part. Okay, so here's this thing. The way that this is drawn or written currently, we have a vertical rectangle. That's the way that this is written because you have dx on the outside, so the little dy, the delta y is the small side of that rectangle. They say, first of all, you should switch the order of the integration. And the reason for this is because this is extremely difficult using this order of integration. So let's try the other way. So let's do it the other way. And the other way means doing this, putting my delta y there. That's the small side of the triangle, or not the triangle, the rectangle. And so setting this up, I have the same integrand, but this becomes dx dy. The dy is on the outside instead of dx because of my rectangle there. Now I just have to think in terms of what would my limits be for this. Okay, so y is the easy part because this little rectangles, they begin with y equals 0. They end with y equals 1. Whoops. Try again. Y equals 1. So just think about where the rectangles begin down here. Chop, 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 chop. They end up there. The slightly harder thing is to think in terms of this inner integral. These will both be functions. And here I will make this really, here I'll just draw like that. It's going from there, so the bottom of the rectangle, or the left side, is that line, which is easy. That's the line x equals 0. The top of that is a little bit harder, the right side. It's that curve. Whoops. Is that the way that works? No, it just stops, doesn't it? Let me try again. There. That curve. So that curve, I need that curve written as x equals something. But we have it here as y equals square root of x. And so we're just going to rewrite that to be x is equal to y squared. And that's what I'll put there. So x goes from 0 to y squared. Now the rest of this is actually quite simple because it sets up a nice substitution. I'll whip it off pretty quickly. So this will be 0 to 1. This is going to be x times this radical because the radical is all constant with respect to x. X goes from 0 to y squared. Then we're going to just, I'm doing this super quick. So then we plug in our limits. You end up with y squared, whoops. I don't know where that 2 came from. Y cubed plus 1. And then from that, I'm going to do a u substitution. I know that excites you all. U is equal to y cubed plus 1. du is 3y squared. dx, sorry, not dx, dy. Just get rid of that whole thing. So I guess I need to be consistent though. So let's do this. Square root of y cubed plus 1. Bear with me a minute. So there's my 3y squared dy. I need to balance out that 3 that magically appeared, and I can do that by putting a 1/3 there. Okay, you probably could do this in your heads at this point. Yes, I can as well. Y cubed plus 1 to the 3/2, and then you have the 1/3 times 2/3. And this is evaluated from y equals 0 to y equals 1. Yeah, sorry if I did that too quickly. Here, I'll do the substitution really quick. This is 1/3 u to the 1/2 du. Okay, so there's the substitution, the purple, and then you know the antiderivative of u to the 1/2 is u to the 3/2 times 2/3. That's it. There it goes. Now plug and chug. What do we got? 2/9. 2/9 times 2 to the 3/2 minus 2/9 times 1 to the 3/2. So I guess this is going to be not 8. 4 radical 2 minus 2 over 9. How's that? Or you could just leave it sort of like this. I don't know. So 2 radical 2 times 2. Yeah, I did too much at once. And then this 2 going along for the right. There. So is this okay? Is there anything else from this homework that caused particular grief that we need to look at? You want to give it, I know you're excited about my diagrams. All right, let's do it. Let's do the diagrams. Or I've got the diagrams for you. You just have to set up the integral. And hopefully it'll work out nicely. I tried. And hopefully, yeah. So I will triple check. When I get to the actual exam, I will quadruple check. But I'll go check it right now to see if it's good. I'll let you know. But I think if I've done it right, that these will come out to be nice answers. So if you get something nasty, just skip it and go to the next one. There you are. I think that's enough. Let me give you another one. Here, you can have all of those. Is this for me? Is that for me? It's not for you. Oh, let's see. If it's labeled, I'll be okay. It's labeled. Oh, you want probability? Later, but not now. Oh no, that's soaking in. Yeah. You don't want to have it. I mean, you can have it for fun if you want. All right, yeah, you should have the one with the triangles. Yeah, I'll put it on the screen so that you can compare in case I gave you the wrong one. Come on. There. Looks some of you are finishing up. So see how we did here. If you're still working, you can. Sure, why not? Excellent. Get rid of it before you change your mind.
I mostly trust myself.
All right, try not to stew too much over this. Put something down, do your best. We get some sort of an answer. Everything's all right.
Yeah, we got home. I haven't actually got my stuff on that folder.
All right, good job. All right, think I got them all now. Does anyone else, other holdouts, savoring the experience? Okay, let me put this together. There, good job. All right, what do I have? This is what I've got. Okay, yeah, I should have told you that you should put a rectangle on there. I forgot, but in the future, if I draw it for you or if you draw it, you should put a rectangle to say, here's how I'm going to integrate this. First one I thought was pretty straightforward. Hopefully it wasn't too bad. Polynomials. The only thing that was bad about it was the numbers got a little bit large near the end, and that caused, I think, some badness. But here's the setup. If you've got this, you've got at least, most of, if you think of it as on the actual test, you're going to have the answer staring you in the face, then this is worth like half credit at least to have the right setup. Maybe I should put parentheses around this. And then doing the work, there's doing the antiderivative. It's a polynomial though, so you just have to sort out the fact you're integrating with respect to y first, treat the x as if it doesn't matter, and then do the x. So here's the intermediate steps, and the answer was 1,000. But I know. It's because of these big numbers. The numbers got really big. You're dealing with, 625? 3 times 625. I don't even know, what is that, 1875? So yeah, so big numbers. But if you've got this, so if you ignore that, I'm like, hey, you got that, you got that, you got that. Oh, you can't add. It's okay. You did great. Okay, so this one, I wanted to have at least one where you were forced into this. You really are forced into this. If you tried to do it the other way, you found out why. Then you can't integrate this if you try it the other way. So I put the delta y there. Here's the setup. So notice that you've got delta y was the small side, so dy is on the outside. There's my limits. And even though I didn't label this, this is the square root of pi here. And this is the square root of pi down here. Anyway, doing the antiderivative, I kind of skipped a few steps. So the inner integral, this is just going to be sine of y squared times x, evaluated from 0 to x equals 0 to x equals y. So it just ends up being y times sine of y squared. And then you have to do a substitution. Here's my substitution, but I got lazy and just skipped ahead to that. And then I plugged in my limits. And here, some of you need to remember that the cosine of pi is -1, and the cosine of 0 is 1. But yeah, after doing it all, I got 1. Final answer. So yeah, so it's mostly arithmetic. If you got here, you've got most of the problem done if you got to here. And then if you got here, you're like, hey, you're practically done. And if I told you the answer was 1, some of you would have been like, oh yeah, I made that little mistake right there, or what have you. So let's go on though. So today we're going to revisit my favorite candy, the dots. I went to Kroger on Friday, hoping to find some dots, like leftover from Halloween. There were none. I had to just get chocolate. So I've got some extra chocolate now in my office. So come to my office, visit, and you'll find in the little containers in the outer office area a bunch of chocolate now. And I can't eat the chocolate, so that's even worse. I did get a few gummy candies, but I'm not putting those in my things. So anyway, this gumdrop, here it is. This is going to be, let me put down the formula here. We'll go to the PowerPoint momentarily. So f of xy is 4 minus x squared minus y squared. This is what this looks like, sort of. I know this is a terrible rendition of this. I probably should just use the computer. So here, this is like that, and then this thing goes up here and down here, whatever. Okay, so you've got this. You can kind of imagine it looks like an old-timey headlight from an old Model T Ford, that sort of parabolic mirror, or a dot candy, gumdrop. Gumdrop would work too. And so I want to find the volume of this thing. And so if you look down on this from above, this thing looks like this. So here's what this looks like from above. Looking down, it's a circle. It's a circle with a radius of 2. Nice circular region. So I don't know if we'll actually finish this one today. I know you're thinking, wait, what? But because this is the setup, so we'll come back to this in a bit. But the point of today is to see that what you can do whenever you have a region that is a nice circular region, or sometimes if the function is such that it dictates that it would be nice to do this, you can take this and do this in polar coordinates. So, I mean, think about what this would mean. Looking at this in terms of rectangular coordinates, let me just show you the difference. Rectangular coordinates, then what you would have to do is you'd have to say, okay, y is between, let's see, what's the top? It's going to be the square root of 4 minus x squared, negative square root of 4 minus x squared, and then x goes from negative 2 to 2. That's painful. I mean, the biggest pain is that y there, having to deal with those radicals. Now, if you think about what this would look like in polar coordinates, you're going to have this. You'll have r is between 0 and 2, and theta is between 0 and 2 pi. It's the same region, it's just way simpler. Now, there is the price. The price you're going to pay when you change to polar form, is that we're going to have to deal with the fact that our points are now polar coordinates. And areas don't work out the same as they do in rectangular coordinates. But that's a low price to pay to have constant limits on my. Let me just show you. It's got to show you how beautiful this is. So back in rectangular land, here's what this would look like. You would have this double integral from, let's see, x is fine. It's the y. The y is so nasty. 4 minus x squared to y equals the square root of 4 minus x squared. And then you've got your function, f, in there, dy dx. So it's those limits are so nasty. And then in polar coordinates, here's what this looks like. So you have 0 to 2 pi, and then 0 to 2 of some function of r and theta now, dr d theta. So as you can imagine, the price that you're going to pay, so notice that you're going from this ugly thing here, terrible limits, to this beautiful thing. Beautiful limits, right? You see limits like that? Oh, you're off scot-free. It's easy. So the price you're going to pay is going to be in this right here. You're going to take a function and you're going to change the function. But even that price, it's going to turn out, is going to be an easy price to pay. Seriously, when we get to the actual nuts and bolts, we might not get to it today. I want to focus on regions right now. But what we'll do is we have to, so essentially what happens is, here we go, we take that function and we change it to polar coordinates. And at first you might go, oh, that's going to be a nightmare. It's not going to be as bad as it sounds. And we have to do a little bit more to it to doctor it up. But it's not hard. Okay, so let's go to PowerPoint land. Where is power? There it is. So here's what we're dealing with. We're dealing with functions in regions that are like this. So we already dealt with a circular region. With a circular region, things are much easier in polar coordinates. But there are other regions that are even worse in rectangular coordinates than a circle. And that's something like this. This is a piece of an annulus. An annulus is like a disc with a hole taken out of the middle of it. So if you imagine the whole thing, it's going to, that would be an annulus. But I've just got the top half of it. If we were to do that in rectangular coordinates, here's what you'd have to do. I just want to point out how beautiful polar coordinates are for something like this. To do this in rectangular, you first of all have to divide this into three pieces, and then do your integral. Then the reason is that if I draw my rectangle, I don't care if you do horizontal or vertical, but the rectangle, the bottom, the base, at least the way I've got this, the base changes from here to here to here. So over here, the bottom of the rectangle is down here on y equals 0. Here, the bottom of the rectangle is on this hump. And then it goes back to y equals 0. So you'd actually have to have 3 double integrals to do that region in rectangular coordinates. But in polar coordinates, this can be written as a single double integral. Notice that the radius ranges from 1 to 2, all the way along that band, from 1 to 2. And theta, the angle, goes from 0 all the way over to pi. So that's one of the main reasons we're going to be interested in doing our double integrals in polar coordinates, is because the regions, if the regions are circular or have round shapes, you're going to want to do polar coordinates. Let's practice this with just a couple more of these. Just a minute, where is my, let's go back here. I'll draw some regions. So give me a sec. And here's what I'd like from you, is tell me what this region would look like in polar coordinates. In other words, what are the values for r and what are the values for theta, the limits. Okay, so let's say that I'm interested in this pi wedge right here. Give me a sec. There we are. And this, and I will just do this in, let's say that this is radical 2, and this is going to be 0, 2. So these here are xy, just so you know. So this is a circle, a piece of a circle, and I'm interested in that pi wedge. So your job is to tell me what the limits are if we switch to polar coordinates. While you're doing that, let me just draw another one of these, just for fun. So that's going to be x squared plus y squared is equal to 4. Oh, I don't like that. Let's make it 9. And this is x. Okay, the second one is going to be a little bit harder than the first one, so I'll need to talk you through that second one in just a minute. Let's deal with the first one, though. So let's see, where are my random people? Just a sec. Randomize. Here we are, Darren. Darren, what do you have for your limits for the r for this first one up here?
0 to 2.
Ah, very good. So r goes from 0 to 2. You'll notice that if this is a circle that is centered at the origin, it has a radius of 2. So that's 2. So the radius, the r, goes from 0 to 2. All right, Madison, what about the theta? What does the angle go from what to what? So the radical 2 over 2 is important. That's actually, so if you're trying to figure out the angle, so you're trying to figure out this angle, so maybe this angle right here, you would do something like this. So I'm guessing this is what you did to get the radical 2 over 2. So I'm curious, what is this angle? And so you can pick one of these, doesn't matter which. I'm going to go with sine because we all like sine better than cosine, don't we? So the sine of that angle is radical 2 over 2. Very good. So you know that that's going to be this angle. This angle here has a sine of radical 2 over 2. So that's probably where you're thinking of that. So Rachel Potts, do you know what angle, can you help her out as to what angle this is that has a sine of radical 2 over 2?
I had
Pi over 4. Yeah, very good. 45 degrees. So that angle there is going to be 45 degrees. 45 degrees or pi over 4. Yeah, why did I write 45 degrees? Because we're in calculus, not physics. Okay, pi over 4. Is that better? All right, now we have to figure. So that gives us our lower limit. So notice that as we're thinking about what angles, so we start and we're like, where does the region start? Oh, it starts here at pi over 4. So that's the beginning of the region. And now we just have to figure out where the region ends, what angle. So let me put this down as the pi over 4 is down there. Now let's find the next volunteer. Joshua, do you know where this region ends? Do you know what this angle is right here? It is pi over 2. Very good. So that's going to be the total. There it is. That's going to be how you would describe that region. Nice, easy. I mean, I know there's a pi there, but that's not that big of a deal. It's a nice constant limits. They're so much better than when you have radicals and whatever else. This would have been, you could do this using a vertical rectangle, figuring out what this is. Y is equal to the square root of 4 minus x squared. This is y equals x. Oh, but it's just so much nicer to have nice limits. Now this next region, this kind of crescent moon shape, I'd like to be able to do in polar coordinates. So let's see if we can work this out together. There's some that I'll have you do and some of it that I will do for you. So the first one is r, and then we'll do theta. So let's deal with r first, and then I'll help you with the bigger one. So notice that if you think of this way, that the r, as you're starting over here at the origin, and as you work your way, it doesn't matter which. So you're on some ray, if you will. So you're on some ray. The first thing you hit is this curve right here. So the lower limit is going to be that curve for r. So r is going outward like this, and this curve here is the first thing that you hit. And I'll bet you can do that one. Briar, what's r for this curve?
X equals.
Yeah, it's this curve, but we want to do it in terms of r, not in terms like what's the radius?
Oh, just
3. Yeah, it's just 3. Yeah. You're trying to make it harder than it really is. Okay, very good. Now we continue. So that's the first thing we hit. And then if you continue outward, the next thing we hit is this curve. Whoops. This one. And that one, I don't even know, because that one gets bigger and then smaller again. So I'm going to need to take this and convert that. But fortunately, I can do this for you. This should be r is equal to, hold on a sec. Let's get this right. 6 times cosine. I believe. Let me double check. Yeah, that's 6 times cosine. Now, you could have done that conversion yourself by taking this and rearranging. It's kind of a pain, but I happen to know this. You'll not have to do these like that sort of a conversion. I just wanted to illustrate that if you had something that you were tempted to use rectangular coordinates for, you could do that. But in your homework, it's laid out a little bit nicer than what I have here. Okay, so what that means is that as you're moving away from the origin, the first thing you hit is this purple curve, which is r equals 3. The next thing that you hit is the green curve, which is r is equal to 6 cosine of theta. And so those will be my limits. So this wasn't quite as nice as the previous problems, but it's not terrible. At least I can do it. I don't even know how I do this with rectangular coordinates. You'd have to divide this into 3 subregions. Yeah, I don't even want to think about it. I just like to do it in polar. Okay, next I need to know the angles. So let's think about the angles. My angles, I'm going to start. Notice that if I had a longer implement, that implement would go all the way to here. That's where the angles start. And then they curve upward. They keep going, and then there they end. So I need to know what this angle is and what this angle is. I'll bet you can guess, but we're going to do it right by doing some, I guess, trigonometry. So let's write these things down. This outer curve is r is equal to 6 cosine of theta. And then the inner curve is r equals 3. So those are the two curves. and I want to find where they intersect. So we can do this. 6 cosine of theta is equal to 3. Take a minute, solve that equation for theta, and that's going to give us the limits for this. All right, Max, do you have a theta, or can you tell me what to do? Ah, very good. So probably, I'm guessing what you did was you said the cosine of theta is equal to 3 over 6, which is 1/2. Very good. And then you happen to know that the angle with a cosine of 1/2 is pi over 3. So this angle, like I said, you probably could have guessed that. So that angle there is pi over 3. It's getting messy. What about the other angle? Well, I guess we can just give up, right? No. We don't have to give up. That's not the only angle that has a cosine of pi or 1/2, right? There's another angle, and that's this angle down here. So you can either write that as, what would that be? 5 pi over 3? Or we could use what would be more useful, and that is negative pi over 3. So that's the range of values. So those are the limits, and I realize those aren't quite as nice as those up there. So, you have nice constant limits up here. Here, it's not quite as nice, but this is so much better than, like I said, I don't even want to imagine trying to do that in rectangular coordinates. Okay, so why are we doing all this? Well, I think just a minute. I think we might be all the way just a sec. I'll show you what your homework is. So I want to make sure we get to the homework. Your homework is up there. It is. Yeah, this is as far as you need to go. It's 1 through 6. And so basically we've pretty much done all the homework, but we need to move on just a little bit further because all of this is just doing the regions. So like, what does this region mean? So do your best to sketch those. And up here, you're just supposed to come up with the region. And these are nice regions. Look at that. I think you can probably, and I think that they mean for this to be a 45-degree angle here. So I think you can all figure out right now what that region is in terms of like R and theta. So that's all you're supposed to do for homework is 1 through 6. But we do have more than that we need to do. Is this where we were? Yeah, there it is. So let's get back to Gumdrop Land and see how we're going to do this. Actually, we won't do that till tomorrow. We need to look at this picture. Okay, so here's the deal, is when you convert to polar coordinates, the price you pay is that things are no longer rectangular. You don't have squares, you have weird pi wedges. So you have things that look like this. If I were to divide this up, if I were to make you do a Riemann sum, that Riemann sum would be a bunch of little weird pieces of pi wedges. And so you'd have these weird pieces, and you would find the volume. So if you imagine, like if you have a volume that you're trying to compute, in rectangular, each of your little pieces that you're adding up are all just rectangular boxes. This is no longer a rectangular box. It's approximately a rectangular box, but it is not a rectangular box. Because it's not a rectangular box, weird things happen when you do the double integral. And so here's what happens is the conversion. So when you convert, so the convert to polar, you throw in an extra r. That's it. So there's a reason for this that we could work out geometrically based on the formulas for the volume of a solid that's not a rectangular solid. But for all intents and purposes, what you're going to care about is you just throw in an extra r. And so here's the formula. So let me just show you the formula. We're going to be using this, and I think we have time. We can do this with the Gumdrop. So check it out. Here's the formula. I know it looks complicated and confusing, but let me explain the important part. The important part is this, that you have a double integral. Let me zoom into the important stuff. Here it is. So you have a double integral where the, whoa, we undo that. I meant to highlight, not to cross out. Okay, you have a double integral where the region is a nice circular chunk. So that's what you have. So R here is a nice circle, or a piece of a circle, a piece of a circle. Okay, yeah, I before E, except after C. I think I just messed it up, didn't I? Yeah, there. You pick how you want to spell peace. You can spell it EA if you want. You know, we need some more peace in our lives, don't we? But anyway, that's a piece of a circle. What piece is it? It's the piece that goes from alpha and beta to here's what you want to think about. Is this sort of thing. So this angle is alpha. This angle up here is beta. This is A and this is B in terms of the radius. So you have this piece of a circle. The A and the B are the radius. The alpha and the beta are the angles. So it would be really nice if you had something that looked like that, a region that looked like that, if we could use polar coordinates. And what this is saying is that you can use polar coordinates as long as you throw in the extra secret sauce. The extra spice that you're going to put in is an extra R. You see the R there? So that's the main thing to remember, is that if you have a piece of a circle, if you convert to polar coordinates, just throw in an extra R for good measure, and you're going to be okay. That's it. The hard part, I think, is just in the execution. And so that's why I've split this up to 2 days. Tomorrow we'll deal with mostly execution, but let's do the gumdrop. I want to know what the volume is. Where is my gumdrop? Did I put it on this page? Yes, it is right there. Okay, let's do this. So what does the problem, it says, if you convert to polar coordinates, which I'm about to do, you throw in an extra R. 0 to 2. So I'm using the limits that you gave me. So you notice that those, oh, I have it written right here, don't I? Well, too late now. Okay, so let's do this. So I throw in an extra R, d theta. So what I have written here isn't quite right. So I need to know what is my function. My function is this. You have 2 options. Well, actually you have lots of options. But the option I'm going to use is I'm going to rewrite this. I need to convert to polar coordinates. And so I guess one of the options would be to just do it with brute force and change the x to r cosine theta and the y to r sine theta and then suffer through a bunch of algebra. But the easy way to do this one, at least, doesn't always work out this easily, but in this case, you might recognize x squared plus y squared from our polar coordinate days, and that x squared plus y squared is r squared, so 4 minus r squared. And it is just that simple. So that's what I'm going to use for my function, 4 minus r squared. Now notice how simple this is. Before is up here with these nasty radicals. You might get away okay with the inner integral, but that outer integral is going to be a nasty thing. Down there, in polar coordinates, there's no radical. That's a polynomial. The limits are constants. Who can ask for anything more? This is beautiful. Okay, so let's do it. It's going to take just a few seconds. In fact, I might even be able to get it in before Joshua has to go and shred. R cubed dr d theta. So this is going to be the integral from 0 to 2 pi of, let's see, this is going to, oh, I should have made you do too late. 2r squared minus r to the 4th over 4, evaluated from r equals 0 to r equals 2. Then, let's see, we'll plug in the limits. So what's that? 4, 8, 4. Okay, so this is going to be the integral from 0 to 2 pi of 4 d theta. I mean, who would have thought, starting out with that, wait, just a second. starting out with this thing up here with all those nasty radicals, that the outer integral is just this. You could probably do this one in your head, I hope. Because it's just going to be 4 theta evaluated from 0 to 2 pi. I'll write it out. But if you're thinking 8 pi, you're right. So that's 8 pi minus 0 pi. Look at that. I mean, so simple. So a gumdrop. Wow, is it time to go already? You guys mutinous here. Oh, well. Yeah, that's all. Yeah, we can do the rest tomorrow, I guess. But yeah, so today's homework is all the basics. Tomorrow we'll deal with stuff like this. But I just wanted to show you, it's so easy once you change the polar coordinates. Look at that. So much better. Stopping the recording.